This video is about our work NaVid, which leverages the vision language model for vision language navigation. During vision language navigation research, we need to define the task. When defining it, there are several key points to consider. Firstly, the task instructions must be in natural language, including landmarks and actions. Secondly, we want the robot to navigate in unseen environments. Thirdly, the robot can carry sensors during navigation, providing visual, depth, and localization information. Additionally, we consider continuous environments where the robot needs to output low-level actions like moving forward, turning left or right, or stopping to navigate in real-world maps. The VLM task is extremely challenging. It first involves a high-level understanding process, requiring the model to comprehend the navigation history and natural language instructions. Additionally, it needs to align the navigation history with the textual instructions. In addition to this high-level understanding ability, the model also needs to master low-level planning skills. The model has to plan paths to approach target locations and avoid obstacles. Overall, the VLM task is highly challenging, involving both high-level understanding and low-level planning. Due to these challenges, related works that consider using simplified settings, top-down maps, and large language models often require many tailored designs. In fact, humans and even some primates can interact with computers to complete given tasks after a certain amount of training. The interaction input consists only of a video and a target, and the operator can complete the task using a keyboard. Can we design a model that, given the corresponding instructions and a video of the navigation process, can choose the next action? Fortunately, in recent years, there has been rapid development in vision language models. Some of these models have demonstrated impressive capabilities in both video and text comprehension. We believe that existing large vision language models have the potential to understand VLM tasks. Using a vision language model offers two benefits. First, it avoids extensive tailored designs and aligns more closely with how humans think about navigation. Second, this approach eliminates the need for depth information, coordinates, and orientation, avoiding the gap between the real world and simulators. Note that the data modality for navigation differs from existing question-answering data, as it contains historical sequences, current frames, and instructions. The current frame information is particularly important as it is used for understanding the current scene and planning the path. Meanwhile, there is significant redundancy in the visual information among the historical frames. This requires a new pipeline for encoding the VLM data. Given the navigation information, NaVid leverages an observation encoder and BERT to encode visual and textual information, respectively. For each historical frame, we use 5 tokens to encode visual information. For the current frame, we use 65 tokens to retain more visual information. For more details, please refer to our paper. To identify the signal source of each part, we referenced the approach used by MiniGPT. We define special tokens to denote different information sources. By utilizing special tokens, we can apply similar methods to process existing QA data, including text, images, and videos. This allows the model to learn from different modalities simultaneously. This approach ensures that our model maintains an understanding of the natural world after training, avoiding overfitting to the navigation task. Finally, the model outputs textual action commands, which include only 4 actions: move forward, turn left, turn right, and stop. Throughout the entire process, the model only needs the corresponding instructions and the navigation history to determine the next action. Another challenge is the current lack of real-world VLM data. Therefore, we consider collecting such data from simulators. We collect VLM data from the R2R training set in the VLNCE simulator. It includes a total of 10,000 trajectories across 61 scenes. We collected 2 types of data: action planning data. Given an instruction, we collected the image sequences from the corresponding navigation trajectory and identified the next action. Instruction inference data. Given the images from a trajectory, we identified the corresponding instruction. We hope this data will help large models learn to align videos with instructions. We collected a total of 320,000 action planning samples and 10,000 instruction reasoning samples. However, during navigation, the navigation history often contains noise or incorrect steps. Therefore, we utilize the Dagger method to collect an additional 180,000 noisy navigation data samples in the simulator. Finally, we used both the navigation data and the multimodal data from VLM as the training data for NaVid. In the results on the R2R dataset, we found that our method performs comparably to the best existing methods. However, our approach relies solely on the navigation video, while the best methods also require noiseless depth maps, precise location information, and orientation data. Under the same setting, where only navigation videos are used, common baselines can hardly complete the VLM task, showing very low success rates. The corresponding performance of NaVid demonstrates the effectiveness of our design and data. In the RxR test set, our method achieved the best performance in unseen environments with more complex instruction data. This also demonstrates that NaVid has strong generalization capabilities. We also study the impact of data on NaVid's performance. We find that NaVid does not perform well with a small amount of data, but its performance significantly improves as the amount of data increases, approaching SOTA levels. Additionally, we observe that the Dagger phase has a very limited impact on the results. We believe this is because Dagger only introduces more diverse trajectories without introducing new scenes and instructions. Therefore, more scenes and instructions may be key to further improving NaVid's performance. Here are some examples of NaVid in real-world scenarios. The first example is very simple. We want it to keep moving forward until it stops at the given target object. On the left, it stops in front of a door, while on the right, it stops in front of a white box. As we can see, NaVid can effectively distinguish between these two different target objects. Notably, the white box did not appear in the VLM training set, yet it was still able to successfully identify and stop at the target. This example is more complex. The instructions require the robot to first rotate and then go to the chair. Therefore, NaVid needs to understand the sequence of actions. Through this experiment, we found that NaVid can understand the order of instructions, distinguish the direction of rotation, and identify the actual target object. We also deploy the TurtleBot to an outdoor environment. This outdoor setting differs significantly in style from the training environment, yet we find that NaVid can still understand and execute the instructions. We also test more complex and challenging instructions. These instructions include multiple target points and actions. NaVid needs to find the target points along the way and complete them in order. In our results, we find that NaVid can effectively understand and follow these longer instructions. It is particularly capable of recognizing objects in the scene such as glass walls and glass doors. To more intuitively test NaVid's ability to align navigation history with instructions, we input a video into NaVid and then require it to respond with the corresponding instructions for that video. These videos include both real navigation videos and simulator videos. In the results, we find that NaVid is able to understand the navigation videos and provide the correct corresponding instructions in many cases. This demonstrates NaVid's ability to comprehend navigation history and align it with textual instructions. Thank you for your time. For more details, please refer to the paper or contact authors.